A supermassive black hole killed its galaxy by starving it to death. Not with violence, not with explosions, just by slowly removing every ingredient needed to make new stars. When star formation stops completely, a galaxy becomes a graveyard drifting through space. Before we examine this cosmic crime scene, drop a comment about where you're listening from tonight. I read every one. They help me understand what draws you to these late-night cosmic mysteries. If these gentle explorations into the universe's darker corners appeal to you, consider subscribing, but only if these quiet journeys through space truly resonate. The evidence awaits. Our investigation begins now. A galaxy floats in deep space. Normal galaxies should sparkle with blue stars. These young stars burn bright and hot. They signal active star formation. This galaxy shows no blue light anywhere. Healthy galaxies constantly make new stars from gas clouds. The gas cools and condenses. Gravity pulls it together. Nuclear fusion ignites. A new star is born. But this galaxy stopped making stars completely. 3 possibilities exist for missing star formation. The galaxy ran out of raw materials. Something disrupted the star-making process, or an outside force stole the gas supply. The galaxy contains plenty of hydrogen fuel. No external thief appears nearby. Only one explanation remains. Something inside heated every gas cloud. The heated gas cannot collapse. No collapse means no new stars. The killer came from within. The galaxy's center holds a monster. Normal black holes weigh a few times more than our sun. Supermassive black holes dwarf their smaller cousins. This one weighs 4 million suns. That mass sits compressed into a tiny region. Matter spirals inward toward the black hole. Gas falling into a black hole should simply disappear. Some black holes work this way quietly. Others put on a spectacular show instead. This black hole creates jets of energy. The infalling matter heats up from friction. Magnetic fields channel the hot gas into narrow beams. These jets shoot away at nearly light speed. They carry tremendous energy across the galaxy. 2 types of black holes exist. Quiet feeders that swallow matter silently. Active monsters that blast energy in all directions. This black hole chose the active path. Jets from the central monster reach every corner of the galaxy. They heat gas clouds that should be cold. Hot gas expands instead of collapsing. The weapon operates across impossible distances. Ancient starlight tells the story of galactic murder. Young stars contain heavy elements from previous stellar generations. Old stars formed when the universe held fewer heavy elements. Each stellar generation should show more chemical enrichment. But the chemical trail stops abruptly. Star formation should continue steadily throughout galactic evolution. New generations replace old ones as they die. The cycle maintains itself for billions of years. This galaxy broke the cycle 10 billion years ago. Several events could halt star formation permanently. A massive collision might disrupt the galaxy. External forces could strip away gas supplies. Internal heating could sterilize star-forming regions. No collision scars appear in the galaxy's structure. No external thieves lurk nearby. The timing points to internal sabotage. The central black hole reached critical mass. Its jets began pumping deadly energy throughout the galaxy. Only ancient stars remain, slowly fading toward darkness. Black holes can kill galaxies in 2 ways. They might swallow all the star-making gas directly, or they might heat the gas until star formation becomes impossible. Direct consumption happens too slowly. Even supermassive black holes eat matter gradually. Heating works much faster and more efficiently. The jets carry energy far beyond the black hole's immediate vicinity. The heating method explains this galactic murder. Gas needs specific conditions to form stars. It must be cold enough to condense, dense enough for gravity to compress it further, and stable enough to avoid disruption. Black hole jets destroy all three conditions simultaneously. They heat gas to millions of degrees. Hot gas expands and becomes less dense. Turbulence from the jets disrupts gravitational collapse. A perfect murder weapon destroys from within. Dead galaxies have a distinctive appearance. Living galaxies glow with blue light from young stars. Pink clouds mark active star-forming regions. Spiral arms sparkle with stellar nurseries. This galaxy shows only red light from ancient stars. Galactic evolution should produce a mix of stellar ages. Young blue stars in the arms. Middle-aged yellow stars like our Sun. Old red giants nearing the end of their lives. The color balance reveals the crime's completion. Blue stars live fast and die young within millions of years. Their absence proves star formation stopped long ago. Yellow stars live longer but will eventually fade. Red giants represent the galaxy's final stellar generation. No new stars will replace them as they die. The galaxy faces inevitable darkness. Its remaining stars will burn out over the next 100 billion years. Each dying star brings the galaxy closer to total extinction. The galaxy faces inevitable darkness as stars burn out one by one. Jets shoot away from the black hole's center. Normal jets should dissipate quickly in empty space. Most energy sources lose power over distance. Their influence weakens as they travel outward. These jets maintain their strength across the entire galaxy. Black holes can handle their energy output in different ways. Some radiate heat that spreads in all directions. Others focus energy into narrow beams. Focused beams travel much farther than scattered radiation. This black hole chose the focused approach. The concentrated jets act like cosmic snow plows. They push against gas clouds throughout the galaxy. The gas gets swept away from star-forming regions. No gas means no raw material for new stars. Two outcomes are possible when jets hit gas clouds. The gas might compress and form stars faster, or the gas might get blown away completely. The jets proved stronger than the gas cloud's gravity. The galaxy loses its star-making fuel to cosmic wind. Heat spreads throughout the galactic disk. Star formation requires gas temperatures near absolute zero. Cold gas can collapse under its own weight. Warm gas expands and resists compression. Every gas cloud burns at millions of degrees. Heat sources in galaxies usually stay localized. Nearby stars warm their immediate surroundings. Stellar explosions create hot bubbles that eventually cool. Normal heating affects only small regions. This heating covers the entire galaxy uniformly. Three mechanisms could create galaxy-wide heating. Thousands of stellar explosions happening simultaneously. External radiation from a nearby quasar. Internal energy pump from the galactic center. No evidence exists for massive stellar explosions. No bright quasars shine nearby. The central black hole provides the only adequate energy source. Its jets carry heat to every corner of the galaxy. Perfect temperature control prevents star formation everywhere. Gas flows should move inward toward the galactic center. Normal galaxies funnel fresh gas from their outer regions. This gas feeds star formation in the spiral arms. The process continues steadily for billions of years. The gas flows have reversed direction completely. Gravity typically pulls matter inward in spiral galaxies. Gas falls toward the center where it can form new stars. Dense regions attract more material over time. Something powerful enough to overcome galactic gravity is pushing outward. Galaxy-scale forces rarely work against gravity. External gravitational fields from nearby galaxies might disrupt gas flows. Internal pressure from stellar explosions could push gas outward. Magnetic fields threading through the galaxy might redirect material. No external gravitational sources appear strong enough. Stellar explosions happen too rarely for continuous outflow. Only magnetic pressure from black hole jets explains the reversed flow. The jets create pathways that channel gas away from star-forming regions. Invisible barriers redirect the galaxy's lifeblood away from stellar nurseries. The black hole cycles between quiet and active phases. Most cosmic phenomena operate steadily over time. Stars burn at constant rates for billions of years. Galaxies rotate smoothly in predictable patterns. This black hole switches on and off repeatedly. Steady energy output would allow gas to adapt gradually. The galaxy might develop stable patterns around constant heating. Life finds ways to work around permanent changes. Intermittent attacks prevent any adaptation. Black holes can maintain steady activity for long periods. They might also undergo dramatic cycles of feeding and fasting. Variable feeding creates unpredictable energy output. Steady black holes allow galaxies to reach equilibrium states. Variable black holes keep their galaxies permanently disrupted. The evidence points to cyclical activity patterns. Each burst of energy resets the galaxy's gas distribution. No stable star formation can establish itself. Repeated disruption ensures no recovery is possible. Matter spirals inward toward the black hole. Infalling gas should heat up gradually as it approaches. Most of the heating should happen very close to the event horizon. The effects should remain localized near the black hole itself. The heating extends thousands of light years outward. Normal accretion creates hot regions only within a few light years of the black hole. Beyond that distance, gas should cool and behave normally. Local heating shouldn't affect the entire galaxy. The friction zone spans most of the galactic center. Two factors determine the size of heating zones around black holes: the amount of matter falling inward, and the efficiency of energy transport away from the center. This black hole processes enormous amounts of matter. Its magnetic fields transport energy with deadly efficiency. The combination creates a hellish region around the galactic core. No gas can remain cool within thousands of light years. The entire central region becomes a stellar graveyard. The black hole's appetite creates a zone where stars cannot be born. The black hole started small billions of years ago. Normal black holes grow slowly by swallowing nearby matter. They gain mass gradually over cosmic time. Their influence remains limited to small regions. This black hole grew explosively in its early phase. Black holes can grow through two main processes: steady feeding on surrounding gas and dust, or dramatic growth spurts from swallowing other black holes. The rapid mass gain points to multiple mergers. Three scenarios could explain the explosive growth. The black hole consumed unusually dense gas clouds. It merged with several smaller black holes in quick succession, or it fell into a region rich with matter. Dense gas clouds alone cannot provide enough mass. Multiple mergers require unlikely cosmic coincidences. The black hole must have formed in a matter-rich galactic center. Early galaxy mergers brought multiple black holes together. Each collision added mass and spinning energy. The monster grew by devouring its siblings. Mass accumulation reached a turning point. Small black holes influence only their immediate surroundings. Their gravitational effects stay localized. They cannot affect entire galaxies. This black hole crossed a deadly threshold. Every black hole has a critical mass for galactic influence. Below that threshold, galaxies can ignore their central monsters. Above it, black holes become galactic tyrants. The threshold depends on the galaxy's total mass. Two factors determine when black holes become dangerous: their ability to launch powerful jets, and the galaxy's capacity to resist those jets. This black hole achieved both conditions simultaneously. It gained enough mass to create devastating jets. The galaxy lacked sufficient mass to contain them. Size became the difference between harmless and deadly. Star formation began declining steadily. Healthy galaxies maintain constant star birth rates. New generations replace dying stars. The cycle continues for billions of years without interruption. The birth rate dropped dramatically over cosmic time. Galaxy evolution typically shows steady or increasing star formation. More gas accumulation leads to more stellar nurseries. Spiral galaxies especially maintain active star birth. This galaxy's star formation withered progressively. Several processes could cause declining star birth rates. The galaxy might be running out of raw materials. External forces could be stealing gas supplies. Internal heating might be sterilizing nurseries. Gas supplies remained abundant throughout the decline. No external thieves appeared in the cosmic neighborhood. The central black hole's growing influence explains the steady decline. Its jets became more powerful over time. Each increase in jet strength reduced star formation rates. Death came slowly, then all at once. All stellar nurseries fell silent. Even dying galaxies typically maintain some star formation. Scattered gas clouds occasionally collapse despite hostile conditions. A complete shutdown rarely happens. No new stars have formed for billions of years. Galactic star formation usually continues at reduced rates even under stress. Some regions remain sheltered from external interference. Final shutdown requires overwhelming force. This galaxy achieved total stellar silence. Complete star formation shutdown needs universal sterilization. Every gas cloud must be heated or expelled. No region can escape the sterilizing influence. The black hole's jets reached every corner of the galaxy. No gas cloud remained cold enough for stellar collapse. The sterilization process achieved perfect efficiency. The galaxy's reproductive system died completely. Only old stars remain burning. Living galaxies contain multiple stellar generations. Young blue giants burn alongside ancient red dwarfs. The mix creates a vibrant cosmic ecosystem. This galaxy contains only stellar retirees. Stellar populations should span billions of years in age. Continuous star formation creates overlapping generations. Healthy galaxies show stars from every cosmic epoch. The stellar roster stops abruptly billions of years ago. Ancient stellar populations can survive in two ways: by continuing to make new stars occasionally, or by maintaining existing stars for extremely long periods. This galaxy chose neither path successfully. No new stellar births refreshed the population. Existing stars age toward inevitable death. The countdown to galactic darkness has already begun. Each dying star brings total extinction closer. No replacement generations wait in stellar nurseries. Time runs out one dying star at a time. The Andromeda galaxy shows early symptoms of galactic murder. Healthy spiral galaxies should maintain steady star formation rates. Their blue regions should glow with active stellar nurseries. Star birth should continue for billions of years. Andromeda's star formation rate has been declining mysteriously. Normal galactic evolution produces consistent stellar birth patterns. External factors might cause temporary disruptions. Internal processes should remain stable over cosmic time. Something inside Andromeda is gradually choking off star formation. 3 factors could explain Andromeda's declining birth rate. Its gas supply might be running low. External forces could be disrupting stellar nurseries. Its central black hole might be growing more active. Gas reserves remain abundant throughout Andromeda's disk. No external disruptors appear in the cosmic neighborhood. The central black hole shows increasing activity levels. Its jets carry more energy than they did billions of years ago. Each increase in power reduces star formation efficiency. Andromeda faces the same fate as our murder victim. Galaxy clusters contain dozens of massive elliptical galaxies. These giant galaxies should sparkle with ongoing star formation. Their enormous gas reserves should fuel stellar nurseries. Active star birth should continue indefinitely. Every elliptical galaxy in the cluster appears dead. Individual galactic murders happen rarely in cosmic history. Mass extinctions require extraordinary circumstances. Cluster-wide killing suggests a coordinated attack. Multiple murderers operated simultaneously. Galaxy cluster environments present unique dangers. Hot gas between galaxies can strip away star-forming material. Gravitational interactions can disrupt galactic structure. Central black holes can grow to enormous sizes. Environmental stripping affects only outer galactic regions. Gravitational disruption creates visible distortions. Every elliptical galaxy contains a supermassive black hole. Cluster environments allow these monsters to grow exceptionally large. Oversized black holes create oversized destruction. Cosmic serial killers eliminated entire galactic communities. Our galaxy's central black hole currently remains quiet. Dormant black holes pose no immediate threat to their host galaxies. They consume matter slowly and produce minimal energy output. Star formation continues normally around sleeping giants. This peaceful situation will not last forever. Black hole activity levels change over cosmic time. Periods of dormancy alternate with phases of violent feeding. Environmental changes trigger transitions between states. Our black hole will eventually wake up. Two events could activate our galaxy's central monster. A massive gas cloud might fall toward the galactic center. Or another galaxy might merge with the Milky Way. Random gas clouds lack sufficient mass to trigger major activity. Galaxy mergers happen predictably over cosmic time. Andromeda Galaxy approaches us on a collision course. The merger will occur in roughly 4 billion years. Combined galactic centers will create feeding opportunities for both black holes. Our galaxy's executioner sleeps, but will not stay dormant forever. Not all galactic deaths result from black hole activity. Central monsters represent just one category of cosmic killer. Other forces can destroy galaxies through different mechanisms. The universe contains multiple paths to galactic extinction. Galaxy collisions create their own form of murder. Peaceful galaxies should evolve in isolation over cosmic time. Their stellar populations should age gradually. Internal processes should determine their ultimate fate. Collisions disrupt this peaceful evolution completely. Galaxy mergers can produce different outcomes. Small galaxies might survive intact within larger hosts. Equal mass collisions could create new hybrid systems. Violent encounters might scatter stars into empty space. Most merger outcomes preserve stellar populations in new configurations. Only the most violent collisions completely destroy galactic structure. High-speed encounters rip galaxies apart entirely. Stars get ejected into intergalactic space. The original galactic structure ceases to exist. Some galaxies die from cosmic violence rather than internal sabotage. Small galaxies throughout the universe continue making stars. Dwarf galaxies should face the same risks as their larger cousins. Their central black holes should eventually grow large enough to sterilize star formation. Size alone shouldn't determine survival. Many dwarf galaxies show no signs of central black hole activity. All massive galaxies contain supermassive black holes at their centers. These monsters grow over cosmic time through gas accretion. Eventually, they should become powerful enough to kill their hosts. Dwarf galaxies break this deadly pattern. Small galaxies might survive through several mechanisms. They could lack central black holes entirely. Their black holes might remain too small for effective killing, or their gas supplies might resist black hole disruption. Most dwarf galaxies do contain central black holes. Gas disruption mechanisms work regardless of galaxy size. The key difference lies in black hole scaling. Dwarf galaxies contain proportionally smaller black holes. These miniature monsters lack sufficient power for galactic murder. Size determines both the killer's strength and the victim's vulnerability. Hubble telescope focused on the suspected murder victim. Living galaxies should display mixed colors from different stellar populations. Blue light indicates young, hot stars. Red light comes from older, cooler stars. Healthy galaxies show both colors. This galaxy glows only red. Normal spiral galaxies maintain active star formation throughout their disks. New blue stars should appear regularly in the spiral arms. The color balance should favor blue light in active regions. Blue light has completely vanished from the entire galaxy. 3 possibilities could explain the missing blue emission. The blue stars might be hidden behind dust clouds. They could be too faint for detection, or no blue stars exist anywhere. Dust absorption creates specific patterns that don't match observations. Sensitivity limits cannot explain such complete absence. No young stars remain anywhere in the galactic structure. The red light comes entirely from ancient stellar populations. Star formation ceased completely long ago. Hubble's autopsy revealed a galaxy that died of old age. The Webb telescope searched for warm gas clouds. Star-forming regions should glow brightly in infrared light. Warm dust and gas emit heat signatures detectable from across the universe. Active galaxies show numerous hot spots. Webb detected almost no infrared emission. Galactic gas clouds typically maintain temperatures suitable for star formation. Even dormant regions should show some thermal emission. Complete infrared silence indicates unusual conditions. The galaxy's gas supply has gone completely cold. Cold gas in galaxies can result from several processes. External forces might have stripped away warm material. Internal cooling could have reduced temperatures, or heating sources might have been eliminated. No evidence exists for external gas removal. Natural cooling cannot explain such uniform temperatures. The absence of heating sources points to black hole shutdown. When jets stop operating, gas gradually cools throughout the galaxy. Cold gas lacks the energy for star formation. Webb found a galaxy frozen in cosmic winter. Radio dishes detected faint signals from the galaxy's center. Active black holes should broadcast powerful radio emissions. Their jets generate electromagnetic waves detectable across cosmic distances. Strong signals indicate ongoing activity. The radio signature appears extremely weak. Supermassive black holes typically maintain some level of radio output. Even quiet periods should produce detectable emissions. Complete radio silence rarely occurs. This black hole operates in stealth mode. Weak radio signals could indicate several conditions. The black hole might be completely dormant. It could be active but pointing away from Earth, or its activity might have decreased dramatically. Dormant black holes produce no detectable radio emissions. Directional effects would still show some scattered radiation. The black hole continues operating, but at greatly reduced power. Its jets maintain enough energy to prevent star formation, but the activity level dropped far below peak output. Radio telescopes caught the killer reducing its signature. X-ray telescopes scanned for hot gas around the black hole. Active galactic centers should blaze with X-ray emission. Superheated matter near black holes glows at millions of degrees. This radiation should be easily detectable. X-rays reveal gas far hotter than star formation allows. JWST temperatures in healthy galaxies rarely exceed a few thousand degrees. Star-forming regions require cool, dense material. Hot gas expands and cannot collapse. Every gas cloud burns at lethal temperatures. High gas temperatures could result from three sources. Recent stellar explosions might have heated the material. External radiation could warm the gas, or internal energy sources could maintain the heat. No evidence exists for massive stellar explosions. External heating sources remain too distant. Internal heating from black hole jets explains the temperature readings. The energy continues flowing even during reduced activity phases. Hot gas prevents any possibility of star formation. X-ray evidence proves the murder weapon still operates. Multiple telescope types observed the same galaxy simultaneously. Different wavelengths should tell consistent stories about galactic health. Visible light reveals stellar populations. Infrared shows gas conditions. Radio and X-rays detect black hole activity. All wavelengths confirm the same conclusion. Scientific investigations require multiple independent confirmations. Single observations might contain errors or limitations. Comprehensive surveys eliminate uncertainty. Every measurement points to black hole murder. Discrepancies between different observations could indicate measurement errors. Telescope limitations might distort individual readings. Incomplete coverage could miss important details. All telescopes show consistent results within their measurement uncertainties. No significant discrepancies appear in the combined dataset. The evidence forms a complete picture of galactic murder. Visible light shows an aging stellar population. Infrared reveals cold, disrupted gas. Radio and X-ray data confirm ongoing black hole activity. Multiple witnesses testified to the same cosmic crime. Young galaxies and their central black holes grew together peacefully. Healthy cosmic relationships should benefit both partners. Black holes should consume excess material while galaxies gain stability. The arrangement should continue indefinitely. Both partners prospered during the early universe. Galaxy formation typically involves chaotic processes in young cosmic environments. Random gas flows create turbulent conditions. Stable structures take time to establish. Central black holes provided crucial stabilization. Two outcomes were possible when black holes first appeared in galactic centers. They could destabilize their host galaxies through gravitational disruption, or they could help organize galactic structure through their influence. Gravitational disruption would prevent galaxy formation entirely. No stable galaxies would exist today. Black holes acted as cosmic anchors during galaxy assembly. Their gravity helped organize gas flows into stable patterns. This cooperation allowed galaxies to grow larger and more structured. The relationship began as a beneficial partnership. The cooperative relationship eventually soared. Beneficial partnerships should continue as long as both sides gain advantages. Black holes should remain content with moderate feeding. Galaxies should maintain adequate gas supplies. Something triggered a shift from partnership to parasitism. Stable relationships require balanced resource consumption. Partners should take only what they need for survival. Excessive consumption threatens the host's well-being. Black holes began consuming resources faster than galaxies could replenish them. Three factors could drive the transition from cooperation to exploitation: External pressure might force increased consumption. Internal changes could alter feeding behavior, or reaching critical mass might unlock new abilities. No external pressures appear in most galactic environments. Internal changes typically happen gradually. Black holes crossed a critical mass threshold that enabled jet formation. Jets provided new ways to influence their host galaxies. The increased power upset the previous balance. Helpful gardeners became cosmic parasites. Every galaxy shows the same mass ratio between stars and black holes. Random cosmic processes should produce varied outcomes. Different galaxies should contain different proportions of central mass. No universal pattern should emerge. All galaxies maintain nearly identical mass ratios. Galactic evolution involves countless variables that differ between systems. Gas supply rates vary significantly. Merger histories follow different paths. Environmental conditions change over cosmic time. Yet the mass relationship remains remarkably consistent. Three processes could create universal mass relationships. All galaxies might form under identical conditions. External forces could regulate the ratios, or feedback mechanisms could enforce the proportions. Galaxy formation conditions vary dramatically across the universe. No external regulatory forces operate on cosmic scales. Internal feedback mechanisms must control the mass relationship. Black hole growth affects galaxy evolution. Galaxy changes influence black hole feeding rates. A cosmic thermostat maintains deadly precision. Dwarf galaxies throughout the universe continue making stars actively. All galaxies should face similar risks from their central black holes. Size alone shouldn't determine survival rates. Universal physical laws should apply equally everywhere. Many small galaxies show no signs of central black hole interference. Galactic physics operates the same way regardless of galaxy size. Gravitational forces scale predictably with mass. Energy transport mechanisms work similarly in all environments. Size creates crucial differences in the host-parasite relationship. Small galaxies could survive through several mechanisms. They might lack central black holes entirely. Their black holes might remain too weak for effective control. Or their structure might resist black hole influence. Most dwarf galaxies do contain central black holes. Structural resistance cannot explain complete immunity. The key lies in scaling relationships between black hole power and galactic mass. Small galaxies contain proportionally weaker black holes. These miniature monsters lack sufficient energy to sterilize their hosts. The smallest victims prove too tough for their parasites. Stars near galactic centers carry records of black hole evolution. Stellar orbits should remain stable over cosmic time. Gradual changes in central mass should affect orbital patterns predictably. The orbital evidence should reveal growth history. Stellar orbits show dramatic changes over billions of years. Stable black holes should produce consistent gravitational effects. Star orbits should follow smooth, predictable paths. Major orbital changes indicate significant mass variations. The central mass increased dramatically over cosmic time. Orbital changes could result from several processes. External gravitational disturbances might alter star paths. Internal mass redistribution could affect central gravity, or the central black hole could have grown substantially. No external disturbances appear in most galactic centers. Internal mass redistribution typically happens gradually. The central black hole must have gained enormous mass through feeding and mergers. Each growth spurt altered the gravitational environment. Stellar orbits record each phase of the transformation. Star paths preserve the killer's growth chart. Star formation peaked billions of years ago across the entire universe. At first glance, cosmic star birth rates can feel like they should increase steadily over time. More galaxies can sound like more stellar nurseries. The universe can seem like it should grow brighter with each passing eon. Instead, star formation has been declining dramatically. Universal processes often look like they should accelerate as the cosmos evolves. More matter accumulates in galaxies over time. Denser environments can trigger increased stellar birth rates. The opposite trend dominates cosmic evolution. Three factors could explain the universal decline in star formation. The universe might be running out of raw materials. External forces could be disrupting galactic processes, or internal galactic mechanisms could be shutting down nurseries. Raw materials remain abundant throughout cosmic space. No obvious external force operates on truly universal scales. Internal mechanisms within galaxies can explain the cosmic decline. Black hole murders have eliminated star formation in countless galaxies. Each death reduces the universe's total stellar output. Galactic murders dim the entire cosmos. The universe grows dimmer with each passing billion years. Cosmic brightness can feel like it should remain stable or increase over time. New stars can replace dying ones through continuous formation. The overall luminosity can seem like it should persist indefinitely. Vast regions of space now contain only fading starlight. Stellar populations naturally age and dim over cosmic time, but continuous star formation can maintain overall brightness levels. Young stars can compensate for aging populations. No young stars emerge to replace the dying ones. Universal dimming could result from several cosmic processes. The expansion of space might dilute starlight. Dust accumulation could obscure stellar emission, or star formation itself could be declining. Space expansion affects light wavelengths, not total brightness. Dust obscuration creates specific patterns not observed. The decline in star formation explains universal dimming. Dead galaxies contribute no new light to cosmic illumination. Only ancient stars remain to shine in murdered systems. Cosmic shadows spread as galaxies fall silent. Imagine a universe where black holes never learn to kill galaxies. All cosmic gas would remain available for star formation. Every galaxy would continue producing new stellar generations. Universal brightness would increase steadily over time. That alternate universe would shine far brighter than ours. Stellar formation efficiency would reach maximum potential in a murder-free cosmos. No energy would be wasted heating gas clouds. All available matter would convert into shining stars. Our universe operates at drastically reduced efficiency. Cosmic brightness differences could arise from several factors. Variations in initial matter distribution might create different outcomes. Alternative physical laws could produce brighter universes, or different evolutionary paths might lead to enhanced luminosity. Initial matter distribution remains essentially identical across cosmic regions. Physical laws operate uniformly throughout space. The absence of galactic murder would fundamentally change cosmic evolution. Continuous star formation would create far more stellar light. The universe would blaze with the combined output of healthy galaxies. We inhabit a dimmed version of cosmic potential. Black holes regulate more than just their host galaxies. Galactic deaths can seem like they should remain isolated events affecting only individual systems. Local murders should not influence cosmic-scale architecture. Universal structure should develop independently. Dead galaxies alter the structure of cosmic space itself. Large-scale cosmic structure depends on matter distribution throughout space. Living galaxies contribute mass and gravitational influence. Dead systems behave differently in cosmic architecture. Galactic murders change the cosmic construction blueprint. Cosmic structure formation could follow several different patterns. Random matter distribution might create chaotic arrangements. Uniform distribution could produce regular patterns, or selective processes might organize matter into specific configurations. Random processes cannot explain observed cosmic regularity. Uniform distribution fails to match actual patterns. Selective galactic death creates organized cosmic structure. Dead galaxies cluster in specific cosmic environments. Their murders follow predictable patterns based on local conditions. Black holes became cosmic city planners. Dead galaxies preview the universe's ultimate fate. Cosmic evolution should continue producing new stars for trillions of years. Star formation should persist until all matter gets consumed. The universe should maintain some level of activity indefinitely. Most galaxies will die long before running out of fuel. Natural stellar evolution would allow star formation to continue for cosmic ages. Gas recycling would maintain stellar nurseries. The universe would remain active for incomprehensible timescales. Black hole murders will end star formation much sooner. Universal death could arrive through several mechanisms. The expansion of space might eventually halt all processes. Matter itself could decay over infinite time, or active processes could shut down prematurely. Space expansion affects cosmic scales, not galactic processes. Matter decay operates on timescales far longer than stellar evolution. Black hole murders will eliminate star formation throughout most of the universe. Each galactic death reduces cosmic activity levels. The universe approaches a state of permanent darkness. Cosmic winter arrives through murder, not natural causes. Two massive galaxies hurtle toward each other through space. Galactic encounters should result in peaceful mergers over billions of years. Gravity should guide the process smoothly. Both galaxies should survive in some combined form. High-speed collisions tear galaxies apart completely. Normal galaxy mergers happen gradually through gravitational attraction. The process takes billions of years to complete. Most stellar populations survive the integration process. Some galactic encounters happen far too quickly for peaceful merger. Three outcomes are possible when galaxies collide at high speeds. They might merge into a single larger system. They could pass through each other with minimal damage, or the collision could destroy both participants. Low-speed encounters typically result in successful mergers. Medium-speed collisions cause temporary disruption. Only extremely high-speed impacts distract structure entirely. Stars get ejected into intergalactic space. The original spiral patterns disappear forever. No recognizable galaxy remains after the collision. Some galaxies die from cosmic violence rather than slow starvation. A small galaxy falls into a massive galaxy cluster. Individual galaxies should retain their gas supplies during cluster membership. Internal gravity should hold star-forming material in place. Galactic structure should remain intact. The cluster environment strips away essential materials. Galaxy clusters contain hot gas between their member systems. This intergalactic medium typically remains invisible and harmless. Small galaxies should pass through it without major effects. The hot gas acts like a cosmic hurricane. Several forces could remove gas from galaxies entering clusters. Gravitational tides might pull material away. Internal heating could expel gas naturally, or external pressure could strip away star-forming materials. Gravitational effects operate too slowly for rapid gas removal. Internal heating requires external energy sources. Ram pressure from the hot intergalactic medium explains rapid gas stripping. Small galaxies moving through cluster environments lose their star-forming materials. No gas means no future stellar generations. Galaxy clusters become cosmic graveyards for smaller victims. The universe expands and separates galaxies from their fuel supplies. Isolated galaxies should maintain their existing gas reserves indefinitely. Internal recycling should provide materials for continued star formation. Self-sufficient systems should survive cosmic expansion. Expansion cuts off external material supplies permanently. Young galaxies receive fresh gas from their cosmic neighborhoods. Intergalactic streams feed matter into galactic disks. This external supply supplements internal recycling processes. Cosmic expansion eventually isolates every galaxy completely. Isolated galaxies could survive through several mechanisms. Perfect internal recycling might sustain star formation indefinitely. Hidden gas reserves could provide backup supplies. Or external connections might persist longer than expected. Internal recycling never achieves perfect efficiency. No significant hidden reserves exist in most galaxies. External connections get severed by cosmic expansion over time. Isolated galaxies must survive on finite internal supplies. These reserves eventually get exhausted through stellar formation and death. Cosmic expansion slowly strangles galaxies through isolation. Massive stars throughout a galaxy explode simultaneously. Individual stellar explosions should have only local effects. Their energy should dissipate quickly in galactic space. Normal supernova rates should not threaten entire galaxies. Concentrated supernova activity can destroy galactic gas supplies. Typical galaxies experience supernovae at manageable rates over cosmic time. The explosions create hot bubbles that eventually cool and collapse. Most galactic gas survives these isolated events. Some galaxies experience supernova epidemics. High supernova rates could result from several cosmic events. Unusual stellar formation patterns might create massive star clusters. External triggers could synchronize stellar evolution, or environmental factors might accelerate stellar death rates. Random stellar formation cannot explain synchronized explosions. External triggers require unlikely cosmic coincidences. Environmental factors in specific galactic regions can trigger massive star formation episodes. These episodes create numerous short-lived massive stars. When they explode simultaneously, the combined energy expels all remaining gas. Stellar suicide bombers can murder their own galaxies. Dark matter halos provide the invisible foundation for galaxy structure. These halos should remain stable over cosmic time. Their gravitational influence should maintain galactic organization. Structural support should persist indefinitely. Some dark matter halos undergo catastrophic collapse. Galaxy formation depends on dark matter scaffolding for structural stability. Visible matter organizes itself within invisible gravitational frameworks. This arrangement should continue throughout cosmic evolution. Halo disruption destroys the galactic foundation completely. Dark matter halos could face several types of catastrophic failure. External gravitational forces might disrupt their structure. Internal instabilities could trigger sudden collapse, or interactions with other halos might cause destruction. External forces operate too slowly for sudden disruption. Internal instabilities require specific triggering mechanisms. Halo interactions during galaxy cluster formation can destroy individual frameworks. When halos merge or collide, smaller structures get disrupted. Galaxies lose their gravitational foundation and disperse into space. Invisible architecture failure brings visible galactic death. Almost every dead galaxy contains a supermassive black hole at its center. Innocent black holes should remain dormant and harmless. They should consume matter quietly without affecting their host galaxies. No evidence of violence should remain. These black holes show clear signs of recent activity. Dormant black holes produce no detectable energy signatures. Their surroundings should appear cold and inactive. No trace of jet activity should persist after billions of years. Hot gas still surrounds every suspected murder weapon. 3 conditions could explain ongoing heat around galactic center black holes. Recent feeding activity might have warmed the environment. External heating sources could maintain high temperatures, or residual energy from ancient activity might persist. Recent feeding requires available matter that no longer exists. External heating sources remain too distant to affect galactic centers. Only residual energy from past jet activity explains the persistent heat. The murder weapons operated at full power for billions of years. Their thermal signatures still mark the crime scenes. The smoking guns remain hot billions of years after firing. Vast gas clouds drift in empty space far from their parent galaxies. Galactic gas should remain bound within galactic boundaries. Gravity should hold star-forming materials in place. No significant gas should exist in intergalactic regions. Enormous clouds float in the cosmic void around murdered galaxies. Normal galactic evolution reads gas through gravitational attraction. Star formation and recycling processes operate within galactic disks. Very little material escapes into surrounding space. These gas clouds carry chemical signatures from their murdered hosts. Intergalactic gas could originate from several sources. It might represent primordial material that never joined galaxies. Stellar explosions could have expelled it from galactic boundaries, or external forces could have stripped it away. Primordial gas lacks the heavy elements found in these clouds. Stellar explosions cannot explain such enormous quantities. Only external expulsion explains both the quantity and composition of intergalactic gas. Black hole jets blew these materials out of their parent galaxies. The expelled clouds preserve evidence of their violent removal. Cosmic exile preserves the evidence of galactic eviction. Ancient stars in dead galaxies carry precise age information. Stellar populations should span a wide range of ages in healthy systems. Continuous star formation should create overlapping generations. No sharp cutoff should appear in stellar age distributions. All stars in murdered galaxies form before a specific time. Healthy galactic evolution produces steady stellar birth rates over cosmic time. New stars should replace aging populations continuously. The age distribution should show smooth transitions. The stellar age record stops abruptly at a precise moment. Sharp cutoffs in stellar age could result from several cosmic events. Massive disruptions might halt star formation temporarily. Environmental changes could alter galactic conditions, or internal processes could shut down stellar nurseries. Temporary disruptions would eventually allow star formation to resume. Environmental changes typically happen gradually. Only permanent internal shutdown explains such precise timing. The central black holes reached critical activity levels simultaneously. Their jets began sterilizing star-forming regions at that exact moment. Stellar clocks stopped ticking at the moment of murder. Shock waves still ripple through space around dead galaxies. Peaceful galactic evolution should leave no trace of violent activity. Energy disturbances should dissipate quickly over cosmic time. No persistent shock signature should remain. Radio telescopes detect ongoing turbulence in supposedly quiet regions. Galactic environments typically achieve equilibrium after major disruptions. Shock waves from ancient events should have faded long ago. Only active processes maintain persistent energy signatures. The turbulence patterns match jet impact signatures. Cosmic shock waves could originate from several violent processes. Galaxy collisions might create lasting disturbances. Stellar explosions could generate persistent turbulence, or jet activity could leave permanent scars. Galaxy collisions create different shock patterns than observed. Stellar explosions produce localized rather than galaxy-wide effects. Only jet impacts explain the observed turbulence patterns. Ancient black hole jets carved channels through galactic gas. These pathways still carry energy signatures from the original violence. Ancient battlefields preserve the scars of cosmic warfare. The oldest stars in dead galaxies contain crucial evidence. These stellar witnesses should have formed under normal conditions. Their chemical composition should reflect peaceful star formation processes. No signs of violent disruption should appear in their structure. Ancient stars show chemical signatures of disrupted formation. Normal stellar formation produces predictable chemical patterns. Stars should contain elements in specific proportions. Violent environments alter these standard compositions. The chemical evidence points to formation during galactic chaos. Unusual stellar chemistry could result from several formation scenarios. External contamination might alter stellar compositions. Unique environmental conditions could affect formation processes, or violent disruption could create non-standard chemistry. External contamination cannot explain galaxy-wide chemical patterns. Unique conditions would affect only limited regions. Only violent disruption during formation explains the chemical signatures. These stars formed while black hole jets disrupted their stellar nurseries. The chaos left permanent marks in their chemical structure. The last witnesses carry murder evidence in their very atoms. Current galaxy murder rates suggest a predictable cosmic timeline. Healthy universes should maintain steady star formation rates indefinitely. New galaxies should continue forming from available matter. Cosmic brightness should remain stable for trillions of years. Many galaxies may die within the next 100 billion years. Universal evolution typically operates on timescales longer than stellar lifetimes. Galaxy formation and death should happen gradually over cosmic ages. No sudden mass extinction should threaten cosmic evolution. Black hole murders could eliminate most star formation much sooner. 3 factors could determine future galactic death rates. Available matter might run out naturally. Environmental changes could alter galactic evolution, or internal killing mechanisms could accelerate cosmic death. Matter supplies remain abundant throughout the observable universe. Environmental changes happen too slowly to affect short-term evolution. Internal black hole activity could eliminate star formation systematically. Each galactic murder could reduce cosmic star birth rates. The killing spree could continue until few living galaxies remain. The universe may face scheduled mass extinction within cosmic centuries. 2 spiral galaxies hurtle toward each other through space. Normal galaxy encounters should result in peaceful mergers over billions of years. Both systems should survive in combined form. Star formation should continue in the merged galaxy. This collision could trigger massive black hole activation. Individual galaxies typically maintain stable relationships with their central black holes. Mergers can disrupt these delicate balances. Combined galactic centers create feeding opportunities for both monsters. The collision will occur in roughly 4 billion years. Galaxy mergers could produce several outcomes for star formation. The process might trigger increased stellar birth rates temporarily. It could maintain current formation levels, or it might shut down star formation completely. Temporary increases require stable gas supplies that won't survive the merger. Current formation levels need undisturbed galactic environments. Combined black holes could consume available matter rapidly and generate devastating energy output. Their jets could disrupt star-forming regions across the merged galaxy. Star formation might not survive the most intense phases of the feeding frenzy. Our galaxy's execution date has already been scheduled. Star formation may largely cease within 1 trillion years. Cosmic evolution should continue producing stellar generations for much longer periods. Internal recycling should maintain star formation indefinitely. Some galaxies should survive as stellar refuges. The universe may contain mostly aging red dwarf stars. Natural stellar evolution allows star formation to continue until all matter gets consumed. This process should take incomprehensibly long periods. Most of cosmic time should feature active stellar nurseries. Black hole murders could end stellar birth zones earlier than natural processes. Universal death could arrive through several mechanisms. Matter itself might decay over infinite time scales. Space expansion could halt all cosmic processes, or active star formation could simply stop. Matter decay operates on timescales far beyond stellar evolution. Space expansion affects cosmic distances, not local galactic processes. One possibility is the cessation of star formation arriving earlier than expected. Black hole murders could eliminate stellar nurseries throughout the universe. No new stars would replace the aging populations. Cosmic darkness may arrive through murder, not natural aging. Supermassive black holes will eventually evaporate completely. These cosmic monsters should persist indefinitely after consuming their galaxies. Nothing should threaten their existence once matter runs out. They should remain as permanent monuments to galactic murder. Quantum mechanics will slowly destroy every black hole. Black holes appear indestructible according to classical physics. Their event horizons prevent any escape of matter or energy. They should grow larger over time through continued feeding. Quantum effects cause black holes to emit radiation slowly. Black hole destruction could happen through several quantum processes. Virtual particle pairs might allow gradual energy loss. Vacuum fluctuations could destabilize event horizons, or unknown physics might operate extreme scales. Virtual particle effects operate too slowly for rapid destruction. Vacuum fluctuations require specific conditions unlikely in most cosmic environments. Hawking radiation will cause all black holes to evaporate eventually. Larger black holes take longer to disappear than smaller ones. The process will eliminate every trace of the cosmic murderers. Even the killers will face cosmic justice through quantum execution. Hypothetical advanced civilizations could theoretically prevent galactic murder. Technological species might develop ways to control black hole activity. They could redirect jet energy away from star-forming regions. Artificial intervention might save condemned galaxies. No evidence exists for such cosmic engineering projects. Advanced civilizations should leave detectable signatures of large-scale construction. Artificial structures around black holes would emit characteristic energy patterns. Modified galaxies should show signs of technological intervention. The universe shows no trace of cosmic-scale engineering. Galactic salvation could happen through several technological approaches. Civilizations might learn to shut down black hole jets completely. They could harvest jet energy for useful purposes, or they might relocate star-forming materials to safe regions. Complete jet shutdown requires understanding of quantum gravity. Energy harvesting needs technology beyond current physical knowledge. Relocating star-forming materials offers the most plausible salvation method. Advanced civilizations could move gas clouds away from jet influence. Protected stellar nurseries could continue operating indefinitely. The universe's only hope lies in technological intervention that may never come.